Hi, my name is Aidana, and today I'm going to explain minimum spanning tree. And here some theory. Minimum spanning tree it's a subset of the edges of a connected, edge-weighted, underrated graph that connects all the vertices together without any cycles and with the minimum possible total edge weight. So it means that we are going to find the minimum possible way between all vertices. So we have different ways to find MST, and one of these primes algorithm. And the logic is we need to find a cut of two sets. One contains the vertices already included in MST, and the other contains the rest of the vertices. Pick the minimum weight H from the cut and include this vertex to MST set. So a table of contents. At first I'm going to show animate, then pseudocode, third one is Java example, which will be by IntelliJ IDEA, and finish. So some animation for visualize. Let's consider that our starting vertex is A, and we have 3 edges for A. We are going to choose edge which has at least weight, and it will be 25. We marked it like blue, and we have here four edges which are in green because we all edges with one end in the blue tree and one end outside. We have edges outside and in the beginning. Here at least weight is 30. Then we are going after 30 we choose 50 because we have, so okay, we take 30, then we have more edges, and at least one was 50. Then we have here two same edges, they are 70, but we choose which was longer. Then we okay, our choice is in green, and we choose the one of least weight and add it to the 3. So it's a 40. Okay. So here we take 70. Then our next most least weight was 38. Then 20. Then 32. And the last one is 35. So here we visit all our vertices and then find minimum weight between them. And the total weight of this tree is 395. Okay. So I'm going to show pseudocode. Here we have S, it's a starting node, then N is our number of nodes, M equals to N minus 1 because it will be number of edges in MST tree. We have edge count, MST cost, because we need to check that they will must be equal to each other. And then we have empty list, MST edges, because we are going to create new one. And with function add edges, we add our first node. Then here we have loop. While our MST tree are not created, we consider that H is our next base age, and the node index it will be it will be age which we consider. Then we have main part is if it was visited, so we are going to skip it. And to our empty age we add new age and update our MST cost. So with function add ages we create 3, and but if our count not equals to number of ages in MST, we are going to return null. Third one is Java example. So okay, I'm going to open my IntelliJ. Okay. And then it's IntelliJ. 1 minute. Okay, we have a class, and it's our lazy print adjacency list, which has static class age, and in the age we have 3 parameters from to cost. Then we have inputs, private final int n, which will be equals to number of nodes and our graph. Then Boolean values, so if it's solved, if our MST3 exists, if visited, and our queue, then outputs which are going to show after run minimum cost sum and our ages. So here we create our graph, and in public age get MST. So we get our ages in MST3, but if they are not ages, we are going to just return null. Then we have function which return cost, and the function add ages which get our ages, but by node index. So if this age not visited, we are going to add. And the main part is solve. So if it was solved, we are going to our Boolean value give true. And here code is the same in priority in pseudo code. M equals to number of minimum span 3. Then we create priority queued. We create our Boolean and the age, and by add age function we give our first age. Then here we have while loop. So age is the next best age, node index. If visited, we skip it. Add to our ages new MST3 new ages. So if we have no ages, we are going to return null. Create empty graph, because we are going to create graph, and add directed age function which will create new ages. So we have lazy prints demo from slides. It's function which create our graph. So if we are going to run it, okay.